Alright, so I decided to make a video that explains why the square root of 5 is a never-ending decimal, and it's the proof of that. So it says prove that square root of 5 is a never-ending decimal. So my start here is that if square root of 5, if square root of 5 has a finite decimal representation, it also must be able to be represented as a fraction of two integers a and b. So that means that square root of 5 has to be equal to a over b, where a and b are both integers. That's the definition of a decimal that is finite. So if we square both sides, we get 5 equals a squared over b squared. And if we times both sides by b squared, we get 5b squared equals a squared. And then if we subtract a squared from both sides, we get 5b squared minus a squared has to be equal to 0. So that's it right there. If we can find two integers where b squared and a squared, and we do 5 times the first one minus the second one equal to 0, then if we put a over b, we could get the square root of 5. So now here's where the hard part comes. Gaussian congruence, that just means that we kind of set all multiples of 5 equal to each other. And it's kind of really hard to explain, but just trust me that it works. So we can remove all multiples of 5 from our equation, as long as we let the right-hand side be allowed to be all multiples of 5. So if we remove 5b squared from the equation, and if we set the right-hand side to all multiples of 5, so if we remove the 5b squared, we're just left with negative a squared is congruent, that's the 3 lines, to the set of all the multiples of 5. So, and because the a is squared, signs don't matter, so a squared is congruent to that set, not negative a squared. So, and also through Gaussian congruence we can assert that the integer solution of a must be in the first set of congruence, which is from 0 all the way up to 1 less of m, and where m is the multiple that we set the right hand side to. So if m is 5 in our case, because we set it as multiples of 5, we did that on purpose because we wanted to get rid of the 5b squared. So, alright, so that means that the integer of a, the solution, must be in the set of 0, 1, 2, 3, or 4. Because from the theorem, it goes from 0 up to m minus 1. m is 5, so it goes from 0 to 4. Those are the 5 possible solutions for a. So we have to test each one, as this is a rigorous proof. So if a is 0, a squared is 0. If a is 1, a squared is 1. If a is 2, a squared is 4. If a is 3, a squared is 9. If a is 4, a squared is 16. So those are all the numbers. So remember from the equation in the above rectangle, a squared must be either 0 or a multiple of 5. So I'll go that's the one in the rectangle. A squared must be either 0 or a multiple of 5, all the way up to infinity. Okay, out of the possible a squareds that we tested above of 0, 1, 4, 9, and 16, 0 is the only one that could possibly work. That's either 0 or a multiple of 5. So 0 is the only possible solution for a. Letting a equal to 0 also forces b to be 0 from the circled equation above. So up to the circled equation, if we set a squared equal to 0, then 5b squared equals 0. If you divide both sides by 5, you get b squared equals 0. You square root both sides, b must be 0. So that forces b to be 0. So from the circled equation above. So letting a and b both be 0 produces a contradiction because 0 over 0 is undefined. Up here, where we have a over b, a and b both can't be 0 because b is on the bottom of a fraction and it's impossible to divide by 0. So, because 0 of 0 is undefined, so that means that 0 does not work for a. So we just tested every single point. 1, 4, 9, and 16 aren't multiples of 5, so those don't work. And 0 is, but it doesn't work because it produces that contradiction. So because there's no possible integer a that exists that satisfies the square root of 5 equals a over b, we can confidently say that the square root of 5, the decimal form of that, goes on forever.